everyone. My name is Matthew Hunter. I work in the Stanford Space Rendezvous Lab advised by Professor Simone D'Amico, and my work is titled Fast Fuel Optimal Constrained Impulsive Control with Application to Distributed Spacecraft. For an overview of my presentation, I'll first go over my goals and motivation for this work, followed by looking at the state of the art. I'll then go over reachable set theory, which is a fundamental methodology used to make the advancements in this work, and expand reachable set theory to a sequential formulation. I'll then constrain each of the reachable sets to produce a computationally efficient solver for distributed space systems, simulate and validate the proposed architecture, and conclude with conclusions in future work. Control of linear time variant systems is a very broad problem applicable to many fields, especially fields that have a limited actuation resource. One such field is spacecraft control, where the onboard actuation resource is propellant, used for propulsive spacecraft control. This propellant can be used as a cold gas thruster or combustive thruster. Either way, these thrusts can be modeled as approximately impulsive or instantaneous maneuvers. Spacecraft control also benefits from orbital motion being accurately characterized by linear models. Even more specifically, spacecraft formation flying in swarms offer additional science capabilities over single satellite systems, but the inclusion of smaller, cheaper spacecraft, as well as multiple spacecraft, introduces additional operating constraints that may be of interest to the control problem, such as limited fuel payload and control authority, guarantees of collision avoidance, and computationally limited hardware. So my problem statement for this work is to design an impulsive maneuver planner that leverages optimality conditions derived from reachable set theory to solve trajectories under both convex and non-convex operational constraints with provable bounded optimality and with limited computational load. Looking at the state of the art for control solvers for both unconstrained and constrained optimal control, they kind of fall into three distinct categories. Closed-form solutions are simple and computationally efficient, but their solutions are often case-specific and can only include limited perturbations and constraints. Closed-form solutions have also been demonstrated on a variety of formation flight missions, such as Prisma and TandemX. Numerical optimization techniques, in contrast, offer a wide generality in control problem and control input variables, but they're very computationally intensive, and there's often no optimality guarantees with the methodologies, such as genetic algorithms or particle swarm tree search. Finally, the most popular approach in literature is indirect optimization because it provides conditions for provably global optimality. It's often a more numerically efficient technique than direct optimization as well, although this can depend on the number of variables considered, as well as the optimality conditions found for the control problem. Indirect optimization techniques can include sequential convex programming, model predictive control, pseudospectral methods, as well as reachable set theory. However, overall, the literature lacks a numerically simple, provably optimal approach for arbitrary constraints, as well as a guarantee or some metric of global optimality without a significant simplification to the control problem itself. So the basis of this work, as I mentioned before, is reachable set theory, which in its simplest, most unconstrained form considers a control problem minimizing the cost of the maneuvers in a control window subject to a linear time variant dynamic constraint. Again, the control actions we're considering for spacecraft control can be considered impulsive, which simplifies both the objective and the dynamic constraint to a simple arithmetic sum of maneuver quantities or functions. The cost is the sum of norm-like cost functions, piecewise defined based on time throughout the control window. The pseudo-state and the dynamic constraint is an invariant of the control problem and is simply the final desired state minus the initial state propagated over the control window. Control actions are similarly translated from the time they occur to the final state, which arrives us at this simple base control problem. Reachable set theory primarily consists of two sets, the set S, which is the set of pseudostates omega, reached by any single action of a given cost in the control window, or S is at specific times, but also can be at times throughout the control window. S star is the set of pseudostates that can be reached by multiple actions of combined cost equal to C. can be shown that S star is the convex hull of maneuvers in S throughout the control window. This then makes lambda a very important quality of the reachable set, because lambda is an outward normal of distinct contour of the convex hull. And this contour lambda is the optimal lambda if it intersects the desired pseudostate at minimum cost. So this control problem we were showing before can be more efficiently solved as its dual, as a maximization problem. We were effectively trying to find this contour of the reachable set that intersects the desired pseudostate at minimum cost. Lambda then will give you both the optimal cost of the control problem as well as the optimal maneuver times and directions throughout the control window, all through one single variable. So reachable set theory alone is not, in its current state, is not enough to accommodate all of these constraints that we're looking, operational constraints that we're looking to accommodate. Specifically, we need to know the trajectory and the relative maneuver timing between maneuvers throughout the control window to know whether or not they satisfy state constraints on the pseudostate trajectory or timing constraints in between maneuvers. Therefore, consider time ordering the maneuvers considered by the reachable set theory throughout the control window. And it can be seen that time ordering these maneuvers means that there's no loss of generality of the reachable sets, because just simply time ordering the maneuvers does not change the shape of the convex hull S star or its contours that may intersect a desired pseudostate at minimum cost. Therefore, the full control problem can be broken down into intersecting waypoint subproblems, where a waypoint is defined as a spot in pseudostate space where the trajectory reaches after the previous control actions in the control window. I'll talk about it in a second. What this means is that you get this optimal overlapping substructure, which is very similar to that seen in dynamic programming and allows the application of the principle of optimality often used in dynamic programming, which means that the full optimal solution for the control problem is comprised of optimal solutions to each one of these subproblems. So you can see this expansion of the full control problem to waypoint subproblems down here has almost the exact same structure as the full control problem shown before, which demonstrates this principle of optimality. This is also displayed by the figures on the right, where if you start at a subproblem at the first time in the control window and you have all the maneuvers open to you, you have the contour intersecting of the convex hull intersecting the desired pseudostate at optimal cost and the resulting optimal maneuver directions and times. If you take the optimal maneuver at T1 and set it at its optimal magnitude, the subproblem at T3 then recovers the exact same lambda, the exact same direction of the optimal maneuver at T3. And so you've then recovered the full optimal control profile. So now that we have this sequential formulation, we want to actually start accommodating operational constraints. This work considers three types of operational constraints. The first being a state constraint, which is an area of pseudostate space, which is inadmissible for the pseudostate trajectory found by the control solver to enter. This can be defined in a non-convex way, it's just a keep-out ellipse, or convexly as a maximum deviation from some sort of nominal state. It's worth noting that the actual definition that's used at each subproblem, waypoint subproblem here, is slightly more restrictive than simply the inadmissible states alone. It's actually any maneuver that acts in the direction of an inadmissible state that is reachable given the current magnitude or cost associated with the subproblem. This is done to preserve the linear scaling of the definition of the reachable sets and the nice qualities that it has. And it can be seen that by varying the cost, you can actually recover the full spectrum of maneuvers on the boundary of any constraint space that you're looking for, simply by varying the size of the reachable set. For maneuver timing in this work is considered as a non-convex constraint, which is set as a minimum time in between two maneuvers happening in the control window. And maneuver magnitude can be realized as a convex upper bound on single maneuver cost. So now that we're including constraints, these constraints can be incorporated into the sequential reachable set formulation at each waypoint, meaning that you're satisfying them at each subproblem location. So now you can solve each one of these subproblems, as I said before, without needing to convexify the full control problem. By solving each one of these subproblems, you can again find optimal maneuver locations and times depending on the location of your waypoint and the resulting optimal lambda. But two gaps have to be addressed to make this into a full control solver. The first is that we don't yet know what the optimal size of each one of these subproblems or the control inputs may be. Specifically, we don't know what the transition between a given subproblem I and the next subproblem I plus one may be, as this is dictated by the optimal maneuver chosen and its magnitude and the resulting waypoint that's created. To meet this gap, we have derived a set of new subproblem optimality conditions in the frame of increasing a maneuver magnitude until it is no longer optimal with respect to the next waypoint of the control problem. And these optimality conditions can be realized as a maneuver is optimal in the next subproblem if it's optimal as defined by lambda, the next subproblem. It acts in the same direction with equal efficiency to a maneuver that's optimal in the next subproblem. And it does not increase the lower bound on optimal cost. Effectively, if any of these conditions are true, the maneuver is still optimal and you have not actually realized the transition between your current subproblem and the next subproblem. The second gap that must be addressed is this constraint. Because we have added so many constraints to the constraint of the control problem, so many operational constraints to the constraint of the control problem, the constraint can no longer be expressed analytically. And actually solving this exactly requires evaluating many maneuver direction samples, which introduces a prohibitive computational load to solve the problem. Instead of doing that, instead of solving this explicitly, consider solving the problem implicitly as a bound on unconstrained optimality loss. You then take advantage of the numerical efficiency of solving the unconstrained problem, and then can simply check an arbitrary number of constrained maneuver samples against a user-defined suboptimality bound that is defined by the user. As long as one of the samples that you have fits within this bound, you've satisfied the constraint. So to build a computationally efficient solver, constraint solver for DSS, it is primarily composed of two algorithms. The first algorithm, which is used by the second algorithm, is rollout, with the goal of optimizing the magnitude of given maneuver direction and time to find this transition between one subproblem and another subproblem. You start with a magnitude of 0, and you increase the maneuver magnitude until the maneuver is no longer optimal at the resulting subproblem. So it's steps of increasing maneuver magnitude, finding the next waypoint, solving the unconstrained control problem, and finding a new set of optimal maneuvers that satisfy the constraints and are within the user-defined suboptimality bound of unconstrained optimality. You effectively continue to increase or roll out maneuver magnitude until a new subproblem is realized. Second algorithm that uses rollout is branching. And the goal of branching is to solve the sequential constrained maneuvering until the remaining control problem can be solved and satisfy the constraints with unconstrained maneuvering. It begins by starting with the unconstrained maneuver plan and checking it against the operational constraint of the control problem. If one of the operational constraints is violated, the constrained maneuver, optimal maneuver defined as above the user-defined suboptimality bound, that is closest to the beginning of the control window, is rolled out, added maneuver plan, and the reduced control problem is found. This sequential time ordering that we've done before can be done either forwards or backwards in time. So to reduce time and make the problem more efficient, we can also do this backwards. So we also roll out the optimal maneuver closest to the end of the control window. We then again solve the unconstrained control problem and check it against the operational constraints and repeat this until the unconstrained maneuver plan meets the constraints and we have a full maneuver plan with bounded optimality that satisfies the operational constraints. While we're doing this, we're also keeping track of the potential optimality that is being lost by the approach. So which can be found at each iteration by increasing this value by the increase in the unconstrained lower bound due to using this maneuver sampling process, as well as the maneuver sample size, C min, used to find the maneuver magnitudes in rollout each time. To simulate and validate this algorithm, I'm going to be using an example test case of distributed space systems, which is defined as deputy relative motion linearized about a non-maneuvering chief reference orbit. These systems are commonly parameterized by relative orbital elements for the deputy state, which are defined on the right there in radial, tangential, normal, relative motion space for bounded relative motion. Each one of the scenarios I'll be showing today consists of a Monte Carlo simulation of 200 runs with randomized pseudostates and operational constraints. The two main scenarios I'm going to be using as kind of illustrative are a walking safety ellipse, which is a change in tangential separation, while accomplishing passive safety with bounded out-of-plane relative motion, and also with primarily, or in this case only, convex operational constraints. The second scenario is the co-elliptic orbit, which will use both convex and non-convex operational constraints. It's also a change in tangential separation between the chief and deputy with minimal out-of-plane motion. The baseline solvers that will be compared against the proposed solver are an unconstrained reachable set optimal control solver, solver within the CVX software package, and an SCP for non-convex constraint areas. So looking at this a walking safety ellipse case, we have the illustrated pseudostate trajectory shown above, and the important metrics of the Monte Carlo simulation shown in the bottom right. Looking above, you can see the KD solver, the unconstrained maneuver plan, clearly violating a convex state constraint as demonstrated by the boundary of Q, where Q is defined as the state constraint. The HD solver, which is the proposed solver by this work, satisfying that constraint, and the solution found by CBX for this particular problem setup. Looking at the Monte Carlo run specifically, there are three important metrics to look at. The first is the ratio of the proposed solver cost to CVX solver cost, which should be finding a optimal solution to this convex control problem. However, when you try to apply CVX to a similar control problem as is found by the HD solver, you'll notice there's a large difference in the min and max costs found by the solvers. And this is because the CVX solver is really struggling to converge to the same accuracy as the HD solver. Using the same, the CVX solver in this case, as we go a bit more into in the paper, is actually using fewer input control variables, even in this case, than the HD solver is. And even at that point, the CVX solver is struggling to converge with the number of maneuver locations and times, as well as the number of constraints of the control problem. The second important metric is this ratio of HD solver costs to the expected cost increase as incurred by the sequential setup. As I mentioned before, we're keeping track of what the worst case increase in optimality could be. We see that this quantity never exceeds 1, meaning that we have successfully guaranteed an optimality bound on maneuver plan cost set by the user. Finally, looking at solver runtimes, the HD solver, proposed solver, is often significantly faster than CVX, with outliers occurring due to naive randomized inputs in the Monte Carlo simulation process, which results in poorly conditioned problems that create many small maneuvers in the sequential setup. Coelliptic orbit is a very similar layout here, where instead the state boundary is a keep out ellipsoid instead of retaining the trajectory inside. Looking at the Monte Carlo simulation again, the HD solver, the proposed solver, finds frequently comparable costs to the SCP and is occasionally more optimal. It's also still guaranteeing and satisfying the user set optimality bound. The big difference here is that the proposed solver often is significantly faster than SCP, with outliers again occurring to naive randomized inputs in the Monte Carlo simulation. So in conclusion, reachable set theory provides insight into the nature of optimal maneuvering, and the sequential approach recovers the optimal cost of unconstrained control within the expected optimality losses of maneuver magnitude optimization. Constraints are implemented at the subproblem level while guaranteeing optimality bounds without having to convexify the full control problem. The proposed solver finds valid maneuver plans within the user-specified optimality bounds with cost comparable to solvers in the literature and significant improvements in algorithmic runtime, especially for non-convex problems. The main future work of this work is robustifying the proposed solver to these naive randomized inputs. This can be done either with a better, more informed solver and control problem setup, or by expanding the branching and bounding technique used by the solver, such as increasing the number of branches explored at each step, such that the solver does not get stuck in places with little controllability. Thank you.